Hello everyone, I am Tanu Sharma and this is audio recording for visually impaired students from chapter Thermodynamics of Physical Chemistry. Thermodynamics, work function and Gibbs function gives free energy. In addition to the various thermodynamic quantities like internal energy, work, heat, enthalpy, entropy, etc., discussed earlier, two more thermodynamic quantities used very frequently in the study of chemical thermodynamics are work function and Gibbs free energy. These are briefly described below. Work function. This is equally usually denoted by the symbol A from the German word Arbeit, which means work and is defined by the equation A is equal to U minus Ts. We heard U is the initial energy of the system, T is the temperature, and S is the entropy. Since U and T and S are the function of the state of the system only and do not depend upon its previous history, therefore A also must be a state function. In order to understand the physical significance of the work function, consider an isothermal change taking place at temperature T then. A1 is equal to U1 minus Ts1 from the initial state, A2 is equal to U2 minus Ts2 from the final state. We here A1, U1 and S1 are respectively the values of work function, internal energy and entropy of the system. In the initial state, A2, U2 and S2 are the corresponding values in the final state. Increased in function A accompanying the process will be given by A2 minus A1 equal U2 minus TS2 minus U1 minus TS1 equal U2 minus U1 minus T into S2 minus S1 or del A equal del U minus T del S. We heard del U is equal to U2 minus U1 is the change in internal energy of the system. Del S is equal to S2 minus S1 is the change in entropy of the system. Now, according to definition to entropy change, we know that del S is equal to Q by T. Further, according to first law of thermodynamics, as applied to an isothermal reversible process, we have del U is equal to Q reversible minus W maximum. Minus sign before W has been used to indicate that work has been done by system during the change under consideration. Putting the values of del S and del U from equation 5 and 6 in equation 4, we get del A is equal to Q reversible minus W max minus T into Q by T or minus del A is equal to W max. Thus, for a process occurring at constant temperature, the decrease in work function A is equal to the maximum work done by the system. In fact, it is for this reason that this thermodynamic quantity has been termed as work function, although at one time it was called Helmholtz free energy. Gibbs function gives free energy. This is usually denoted by G and is defined by equation G is equal to H minus Ts, where H, T, and S are the heat content, temperature, and entropy of the system respectively. H before, since H, T, and S are the functions of the state, therefore G is also function of the state of the system only. Hence, for the isothermal process occurring at temperature T, we can write G1 is equal to H1 minus Ts1 for the initial state, G2 is equal to H2 minus Ts2 for the final state, G2 minus G1 is equal to H2 minus Ts2 minus H1 minus Ts1, H2 minus H1 minus T into S2 minus S1. Del G is equal to del H minus T del S, where del G is equal to G2 minus G1 is the change in Gibbs free energy of the system. Del H is equal to H2 minus H1 is the enthalpy change of the system, and del S is equal to H2 minus S1 is the entropy change of the system. The physical significance of Gibbs free energy is at constant temperature del S is equal to Q by T by definition of entropy change. T del S is equal to Q reversible at constant pressure. Del H is equal to del U plus P del V by definition of enthalpy change. Substituting the values of T del S and del H, we get del G is equal to del U plus P del V minus Q, which is equal to del U minus Q reversible plus P del V. Now, according to first law of thermodynamics, del U is equal to Q reversible minus W max. Minus sign before W indicates that work is done by the system. Substituting this value is we get del G is equal to minus W max plus P del V. Del G is equal to W max minus P del V. But P del V is work of expansion done by the system corresponding to the increase in volume del V, as W max minus P del V stands for the maximum work other than the work of expansion. This is called the maximum net work available from the process. Hence, we conclude that for a process occurring at a constant temperature and constant pressure, the decrease in Gibbs free energy is equal to the maximum net work obtainable from the process. That is the total work minus the pressure volume work or work of expansion. It is because the change in G is a measure of the usual work done that G has been called as the free energy. It may be further mentioned here that it is customary to refer to Gibbs free energy simply as free energy. The designation Gibbs free energy or Helmholtz is added only when necessary for clarity. Variation of Helmholtz function function with temperature and volume. The work function is given by the equation A is equal to U minus Ts, dA is equal to du minus Tds, ds is equal to del Q by T. Further, from first law of thermodynamics, we have del Q is equal to du minus del W. And if the work is restricted to the work of expansion only, minus del W is equal to PdV. Putting this value in equation 4, we have del Q reversible is equal to du plus PdV. Putting this value in equation 3, we get ds is equal to du plus pdv by t, tds is equal to du plus pdv. From this, dA is equal to du minus pdv minus sdt equal minus pdv minus sdt. If temperature is kept constant, then del A by del V is minus P. If volume is kept constant, then del A by del T is equal to minus S. The change in work function for a complete process under isothermal conditions can be calculated as follows. For an infinitesimal change under isothermal conditions, equation may be written as dA is equal to minus PdV. For a complete process under isothermal condition, when the volume changes from V1 to V2, we will del A is equal to integration V1 to V2 into PdV. Putting PV equal nRT, P equal nRT by V for n moles of an ideal gas, we get del A is equal to integration from V1 to V2 nRT by V dV. Del A is equal to minus nRT ln V2 by V1. Del A is equal to minus W max. Variation of Gibbs function free energy with temperature and pressure. The free energy is given by G is equal to H minus Ts. By definition of enthalpy, H is equal to U plus PV. Putting this value in equation 1, G is equal to U plus PV minus Ts. Equation 3, complete differentiation of this equation gives dg is equal to du plus pdv plus vdv minus tds minus sdt. ds is equal to del Q by T equal du plus pdv. Substituting value of equation, we obtain dg is equal to du plus pdv plus vdp minus du plus pdv sdt. So dg is equal to vdp minus sdt. This is an important expression which gives the change in free energy with change in pressure and change in temperature in a reversible process. Equation 6 is called total differential equation. If temperature is kept constant, dt equals 0, equation 6 takes the form dg is equal to vdp, del g by del p equal v. If pressure is kept constant, dp equals 0, equation 6 becomes dg is equal to sdt. Equations 8 and 9 give the variation of free energy with pressure and temperature. The change in free energy for a complete process under isothermal conditions can be calculated as follows. For an infinitesimal change under isothermal conditions, equation 7 may be written as dg is equal to vdp. For a complete process under isothermal conditions, when the process changes from P1 to P2, we will have del G equal integration limit P1 to P2 vdp. Putting PV equal nRT, that is V is equal to nRT by P. For n moles of ideal gas, we get del G equal nRT by P dP equal nRT integration P1 to P2 dP by V. P equal nRT ln P2 by P1. Further, as an isothermal process, P2 by P1 equal V1 by V2. Substituting this value in equation 12, we get del G equal nRT ln P2 by P1 equal nRT ln V1 by V2. Criteria for feasibility spontaneity of a process. As already discussed in section 2.6 and 2.7, the net entropy change for the combined system and the surrounding can be taken as a criteria for the feasibility or the spontaneity of a process. The result right here. If del S system plus del S surrounding is greater than 0, process is irreversible. It is spontaneous. If del S system plus del S surrounding equals 0, the process is reversible. The system is in equilibrium. The above two results may be combined and put in the form del S system plus del S surroundings greater than equal to 0, where the sign greater than refers to an irreversible process and the sign equal to for a reversible process for the state of equilibrium. The above criteria, however, requires knowledge of both del S system and del S surrounding, which is not convenient. Hence, a number of other criteria which require the knowledge of the change in some thermodynamic quantity of the system only are preferred. These may be derived as follows. For an infinitesimal process, the above criteria may be written as ds system plus ds surrounding greater than equal to 0, where the sign greater than stands for irreversible process and the sign equal for reversible process. Further, according to first law of thermodynamics, del gap is equal to du plus pdv, ds is equal to minus du plus pdv by t. Substituting this value in equation 2, we get ds minus du plus pdv by t greater than equal to 0. tds minus du minus pdv greater than equal to 0. Equation is the basic which leads to a number of criteria for predicting the feasibility of a process. In this equation, the sign equal to stands for the reversible process and the sign greater than for irreversible process. In terms of entropy change of the system, if the internal energy and the volume of the system are kept constant, du0 and dv0, the equation becomes dsuv greater than equal to 0, where the sign equal to is for reversible process and sign greater than for irreversible process. In terms of internal energy of the system, the entropy and the volume of the system are kept constant, and then the equation becomes 0 is greater than du at constant s and v, where the sign stands for the reversible and the sign equal stands for reversible process and sign less than for irreversible process. In terms of enthalpy change of the system, by definition of enthalpy H, we know that complete differentiation of this equation gives equation H equal U plus PV. Differentiation dH is equal to du plus PdV plus VdP. Du plus PdV equal dH minus VdP. Putting this equation, this value in equation 6, we get TdS greater than equal to dH minus VdP. If entropy and the pressure of the system are kept constant, ds equals 0 and dp equals 0, so that 0 is greater than dh. dh is less than 0, where the sign equal refers the reversible process and the sign less refers to the reversible process. In terms of change of work function of the system, a is equal to u minus ts. Differentiating this equation completely, we get dA equal du minus tds minus sdt. Tds is equal to du minus sdt minus dA. Putting this value in equation 6, we get sdt plus dA is less than or equal to minus pdv. If temperature and volume of the system are kept constant, dt 0 and dv 0, so that we have dA less than or equal to 0. In terms of free energy change of the system, by definition, free energy is given by G is equal to H minus Ts. H is equal to U plus PV. G is equal to U plus PV minus Ts. Complete differentiation of this equation gives dG is equal to du plus PdV plus VdP minus TdS minus SDT. dE plus PdV is equal to dG minus VdP plus TdS plus SDT. Putting this value in equation 6, we get TdS greater than dG minus VdP plus TdS plus SDT. 0 is greater than dG minus VdP plus SDT. dG minus VdP plus SDT is less than or equal to 0 if pressure and temperature of the system are kept constant, dP0 and dt0, so that we obtain dG is less than or equal to 0. Whereas before, the sign equal refers to the reversible process and sign less than refers to the reversible process. The criteria in terms of free energy change is most significant because most of the process take place at constant temperature and pressure. This criteria implies that if dg is less than 0, the process is irreversible. dg equal to 0, process is reversible. dg greater than 0, the process does not occur. Limitation of the criteria for spontaneity. Note out the various criteria discussed were helpful in predicting the spontaneity of a process, but they do not tell anything about the following: the extent to which reaction takes place, the rate at which reaction proceeds, the mechanism by which reaction proceeds. Advantage of free energy criteria over entropy change. An important advantage of free energy criteria over the entropy criteria lies in the fact that former requires free energy change of the system only at constant P and T, is not concerned with what is happening to the surroundings, whereas the latter requires the total energy change of the system and the surroundings, that is for the process to the spontaneous. Del S is equal to del system plus del S surrounding must increase. Gibbs-Helmholtz equation. The Gibbs energy is given by the equation G is equal to T H minus Ts. Hence, for an isothermal process, we can write G1 is equal to H1 minus Ts1 for the initial state, G2 is equal to H2 minus Ts2 for the final state. Subtracting equation 2 from the equation 3, we get G2 minus G1 equal H2 minus Ts2 minus H1 minus Ts1 equal H2 minus H1 minus T into H2 minus S1. Del G is equal to del H minus T del S. Del G is equal to G2 minus G1 is the change in free energy of the system. Del H is equal to H2 minus H1 is the change in enthalpy of the system. Del S is equal to H2 minus S1 is the entropy change of the system. Taking up equation 1 again and putting H is equal to U plus PV, we get G is equal to U plus PV minus TS. Differentiating this equation completely, we get dG is equal to du plus PdV plus VdP minus TdS minus SdT. ds is equal to Q reversible by T. du plus PdV by T. Q reversible equal du plus PdV by first law of thermodynamics. TdS is equal to du plus PdV. Substituting this value, we get dg minus VdP minus SdT. If pressure is kept constant, dP 0, then del G by del T equal minus S. Subtracting 8 from 9, del G2 by del T minus dG1 by del T is equal to minus S2 minus into minus S1, or which is equal to minus S2 plus S1 if, and equal to minus del S. Or it may be written as del into delta G by del T equal minus del S. Substituting this value del S in equation 4, we get del G is equal to del H plus T del into delta G by del T. This is most common form of Gibbs-Helmholtz equation, starting with the expression for work function U minus Ts and proceeding exactly in a similar manner as above. The following analogous expression can be derived: del A equal del U plus T into delta I by del T. This is another form of Gibbs-Helmholtz equation. Further, sometimes Gibbs-Helmholtz equation is put still in another form, which is derived from equation as follows. Dividing equation 11 throughout by t square, we get del G by del T square equal del H by T square plus 1 by del T. Del into del G by del T 1 by T, del into delta G by del T minus del G by T square is equal to del H by T square. It may be noted that all forms of Gibbs equation inverse quantities like del G and del H, which are state function, do not depend upon path followed. Hence, Gibbs-Helmholtz equation is general equation applicable to reversible as well as irreversible process. Application of Gibbs-Helmholtz equation. One of the application of Gibbs-Helmholtz equation is that knowing the free energy change at any two different temperatures, the enthalpy change accompanying the process can be calculated. However, the most important application of Gibbs-Helmholtz equation is in the study of galvanic shells, which is briefly explained below. When a redox reaction Zn plus CuSO4 gives to ZnSO4 plus Cu is allowed to take in a single beaker, heat is heat evolved. Gibbs and Helmholtz by stating that electrical energy produced was equal to decrease in the free energy accompanying the cell reaction. Electrical energy produced by cell is equal to NFE, decrease in free energy, minus del G is equal to NFE. Substituting this value in the Gibbs-Helmholtz equation, we get minus NFE is equal to del H plus T into del minus NFE by del T. Thus, knowing the temperature coefficient of the EMF of the shell, that is del E by del T. Del H can be calculated if E is known or vice versa. Evidently, the electrical energy produced NFE is equal to the heat evolved only when del E by del T equals 0. Nernst heat theorem. W. Nernst made a detailed study about the variation of enthalpy change and free energy change of a system with decrease of temperature. The result thus obtained is called Nernst heat theorem and is briefly described below. According to Gibbs-Helmholtz equation, del G is equal to del H plus del T into del into delta G by del T. From this equation, it is evident that at absolute 0, when T equals 0, del G is equal to del H. This means that del G and del H are not equally at the absolute 0, but values approach each other in the vicinity of this temperature. The result is known as Nernst heat theorem, that is limit T tends to 0 and d into del G by dt equal limit T tends to 0 d into del H by dt equals 0. Graphically, the result may be represented as shows in this figure. Combining these results in equation 1, we get limit T tends to 0 del S equals 0 and limit T tends to 0 del C is equal to 0. Since gases do not exist at the absolute 0, this means that heat theorem is not applicable to gases. Similarly, it has been found to be inapplicable to liquids also. Third law of thermodynamics. The results of Nernst heat theorem led to a generalization which has been called as third law of thermodynamics. In other words, third law of thermodynamics follows from the results of Nernst heat theorem as briefly explained below. According to Nernst heat theorem, the Cp approaches 0 at 0K. This implies that at 0K, the heat capacities of the reactants and products become equal. It is found that heat capacity of solids tend towards 0 at 0K. This generalization is known as third law of thermodynamics. Every substance has finite positive entropy, but at absolute zero temperature, the entropy may become zero, and in fact, it does become zero in case of perfectly crystalline solids. Importance of third law, evaluation of absolute entropies. The importance of third law lies in the fact that it helps in calculation of the absolute entropies of the elements or chemical compounds. The entropy change is given by ds is equal to del Q by del T. Substituting this value in equation 1, we get ds is equal to Cp dt by T. Now, according to third law of thermodynamics, S0 is equal to 0. Thus, the evaluation of entropy requires the measurement of the heat capacities at different temperature down to 0K. If V corresponds to temperature T1, C corresponds to temperature T, and remembering that A corresponds to 0K, integral given in equation 3 can be split into two parts as follows. St is equal to integration limit tends to 0 to T1 Cp by T dt plus integration limit tends T1 to T Cp by T dt. Hence, this equation becomes St is equal to A T1 cube by 3 plus Cp by T dt. Further, as Cp is equal to AT cube, therefore AT cube by 3 equal 1 by 3 Cp at T1. This means that entropy change from 0K to T1. It is important to remember that calculation as described above are applicable only to a solid involving no polymorphic change. For liquid and gaseous substances, the total absolute entropy of the substance at given temperature will be the sum of entropy changes which the substance has to undergo in order to reach that particular state starting from the crystalline solid at absolute zero. The entropy of each crystalline solid from T0 to T equal Tf, the melting point or fusion temperature. The entropy of fusion or fusion del F by Tf, where del Fh is the latent heat of melting fusion. The entropy of heating the liquid from Tf to Tb, the boiling point. The substance is solid. The temperature at temperature T, only first term is to be taken, Tf equal T. The substance is liquid at temperature T. The first three terms are to be taken with T equal T. The substance is gaseous. Full equation is to be used. Temperature The calculation of standard molar entropy of nitrogen gas at 25 degrees Celsius is illustrated with a given data. Temperature 0 to 10 K, calculation involved, and entropy change joule per Kelvin per mole. 0 to 10 K divide extrapolation 1.92, 10 K to 35.6 K graphical integration 25.25, 35.6 K phase transition 6.43, etc. Test of the third law of thermodynamics by calculation of equilibrium. The equilibrium constant is related to standard free energy change according to the equation del G dot is equal to RT K. The standard free energy change is related to standard enthalpy change, which is del G is equal to del H dot minus T del S. By comparing with entropies calculated from mechanics, the absolute entropy is calculated on the basis of third law found to be complete agreement with those calculated using statistical mechanics. By proving that different allotropical form of substance have equal entropy, absolute zero.